Hello, welcome to your AP Chemistry Summer Review. This is our first part in this little series of trying to get you ready for heading into AP Chem at the end of the summer. And today we're just going to look at some very basic concepts, specifically what is science, a little bit of how we measure, things that you're going to be using all year, whether you realize it or not. As we go through the different topics, these form a basis for what we do later in the year. And honestly, this is stuff you've had for quite some time. You probably had it all the way back in physical science. You probably even had some of this in elementary school and before that, but it's still things that after a summer of being away or doing something else or wherever you're coming from, you kind of can forget sometimes, and it gives us a good basis to move forward. So let's go ahead and get started, all right? What is science? So of course you have to go back to how we define science, and the problem is that we always want to start with how we define science, and yet how we define science can be a little hard to define. If you look in different textbooks might say something slightly different. A lot of them though have the same general themes and key ideas that they need to hit. So I'm not going to make you memorize a science definition necessarily, but I would want you to be able to explain it in your own words and to make sure you can explain these concepts that I've given to you here. Okay? So of course, if you want to study science, what do scientists do? Well, we do a lot of study, we do a lot of research, we do a lot of field experiments, we collect data, we analyze that data, we try to make reports on it to come up with theories and things like that. But a lot of that can sum up to one thing, and that would be called hypothesis testing. Okay, hypothesis, I put here, I just gave you really short definitions and really descriptions, or not even definitions, of these topics. You might want to go back and get longer definitions of them, but for hypothesis, I put proposed idea. Most of you probably will tell me a hypothesis is a educated guess, right? That's a good way of saying it. It is educated in the sense that we're going to research it first. We're going to try to learn as much as we can about it already. What do we already know about this topic? And then guess because we don't know for sure. So if you have a hypothesis, that means you need to test that idea. It might be good, it might not be good, it might need to be changed, discarded, whatever. So it's a pretty tentative idea, a proposed idea. Hey, this is what I think might happen. This is, I think, the relationship between these two things, and then we need to test it and find out. So I'm going to use my work as an example. This summer working on my master's class and completing my research project for my master's in biology, and I'm working with the lakes around my house, and my hypothesis is that increased rainfall, so more rain, will lead to increased levels of phosphorus and nitrates in the lakes. That's my hypothesis, and actually, I've had a lot of trouble with that hypothesis. So far, I haven't really been able to get any evidence for it, mostly because it has not rained yet this summer. It's been a very, very dry summer up here. But anyway, that's my hypothesis, and I'm going to go out and try to test that hypothesis, okay? So we say it as a statement, like, here's what this is. Increased rainfall leads to increased phosphorus in the lakes, but I don't actually know for sure if that's true, or even if there's evidence to support it, and then I'm going to go try to support it. So a theory is what comes about. Theories can come about in one of two ways. They can come about from having many different hypotheses, like, hey, maybe I test my hypothesis and it seems to hold true. I seem to get some data for it. And then I test more hypotheses about bacteria in the lakes, and more hypotheses about amount of rainfall and type of soil and water runoff. And all of these hypotheses together, I then could start to have a theory of how the lakes interact with their environment, with the land around the lakes. And so that might be a theory of, I don't know what you would call that theory, maybe, lake geology or lake ecology or something like that. So many hypotheses join to make that theory. It also can work the other way. Sometimes a theory really does start more as an idea. Like, here's my big idea. What if this happens because of this? What if lakes start to turn green because they have so much extra nutrients in them that then you have an algae bloom and then you have this and you have this? But that was my original theory, that idea. Okay, and I really don't know if it's true at all, and then I start testing it to back it up. So it can come either way. You can either have a bunch of hypotheses and you sort of put them all together and try to form one coherent theory, or you can start out with that sort of theory, and sometimes in history, people have done this. The Greeks love to do this. Just come up with a theory. They didn't have any proof for it, but here was their theory of how, atoms worked and things like that. And then later you get the proof for it, okay? But typically, if you're really going to have it like in a science textbook, a scientific theory, it's got quite a bit of backing behind it in order to be that theory, but it's not necessarily going to be true. Big deal of theory is that it can explain, okay? It's an explanation. It's going to attempt to put all the little details together and tell us why. If a theory can't explain, a theory is useless. And a lot of times that's how they end up getting discarded, is according to this theory, this should happen. This is why this happens. This is how this happens. And then as more time goes on and you do more and more work with it, that theory is no longer explaining what we're seeing. It's no longer explaining what we're observing. At that point, you either throw out the theory or you modify it or try to come up with a new one or something along those lines. There's many examples of this in history, like the phlogiston theory and the theory of the humors in the body, the 4 humors, and they did all the things, and theory of bloodletting and those sorts of things. They were theories we held for a long time. They tried to explain something that we saw in the world, but as we got more data, they didn't explain anymore. And so they are now a thing of the past. We don't believe those theories anymore. Okay? A law generally isn't like that. A law is a statement or equation. It is often mathematical. It does not have to be. So a lot of times you can state a scientific law as a mathematical relationship. Not always, but most of the time, yeah. Okay, so like Kepler's laws of planetary motion, there's actually a mathematical relationship that goes with each one of those. And these are not necessarily explaining why, but they're saying this happens. And every time we look at it, this happens. So laws don't usually change. We have laws that we've had since the time of the Greeks, even maybe before that, and they haven't really changed since then. But that doesn't necessarily mean we know why they happen, just that they do. Gravity is an excellent example, okay? The law of gravitational attraction. We know that it happens. We can put math to it. We have a mathematical representation of that law. But why is there gravity? And that question we still are not quite sure. So the law of gravitational attraction is different than the theory of why gravity works. Theory is up for question. Law, not so much. We don't usually change laws. All right, big ideas in science, and I'm skipping many, many things here, but we'll just hit the big stuff. If you're going to be a scientist, you better be ready to do experimentation and observation, okay? That you're willing to go and observe the world around you and that you experiment on that. And this is where philosophy is different than science. Philosophy tends to do a lot of thinking and thought experiments and that sort of thing, but scientists go out and get more data and try to find it, which is why another example I'll use is this summer is summer 2020 when I'm recording this. And so COVID-19 has been a huge deal now for months, and that was really a big problem at the beginning, is that it started coming out and everyone turned to the scientist and said, hey, what do we do about this? And really the scientists didn't know because we didn't have data yet. And we didn't have time to, it had just showed up. We didn't have time to run tests. We didn't have time to do all these things. And so we don't have that data until we go and get it. We can't just make it up on the spot. Okay? Because of that and many other reasons, science is limited. Many ways. You've probably seen long lists before of how science is limited, but you need to keep that in mind. People forget that all the time, especially with this whole COVID situation. A lot of people turn to science and they want science to give them the answers. And they get disappointed because science can't, okay? That's one of its limitations is I can give you all kinds of data, I can give you all kinds of theories. But I put it down here. It provides data and theories, not truth, okay? I can't tell you for sure this is true, or specifically, this is what you should do. It does not hit morality. So I can tell you that, guns kill people. I can tell you that this drug is bad for your health. I can show you the data and all that stuff. But I can't say if you should or shouldn't pick up that gun, or you should or shouldn't take that drug. But I can tell you what will happen if you do. So those decisions of here's the data, here's the theories, but what do we do with that data? What do we do with those theories? Those decisions are up to people. And if you believe in the Lord, then hopefully you let the Lord influence your decisions. But science can't make those for you. And a lot of scientists try. They want to do the data and also make this is what the world needs to do right now. This is the best policy. Technically, science doesn't do that. Okay, it gives you the data, but it doesn't tell you what to do with it. So people decide what to do with it, and that's where the argument comes in. If you have a well done experiment, and here's your data, and you've shown how you've done it and why you've done it that way, and it's logical and orderly, not that many people are going to argue with your data, as long as you can back it up. But what they probably will argue with is how you interpret that data. And I can show you many, many, many examples of that, okay? And then affected by your worldview. And chemistry maybe isn't as big with this one, but it is still there for sure. And we'll work on this year some article summaries, and I'll bring articles into class and things and look at, okay, here is the data, but then here's how these people view that data. And it's good for you to be aware of your own worldview. I'm sure you know mine. I am actually a biblical creationist. I believe in God, and so that doesn't change the data of science, but it will sometimes change how I interpret that data, because I see chemistry, I see the world as being made by God, and therefore something that is orderly, something that makes sense, something that brings him glory, but also possibly something that we are not going to understand everything about, because the Lord has made it. But there's a lot we can understand. There might be a few things we can. I'm not actually sure where that line is, but that's my worldview of it. Okay, that would be different than someone who views chemistry as just something that happened to be, that came about, or the product of laws of nature entirely. So a little different reason for why I do what I do. But the nuts and bolts of how chemistry works doesn't really change either way you look at it. Okay? All right. That's science. So continuing on here, the scientific measuring. So this is a big deal. You're going to have a lot of labs this year, and labs are a big part of your grade. Definitely need to make sure that you are comfortable making measurements, and I'm going to assume that you can. Now, I'll help you with some of the harder ones, but your basic measurements, like this here's a graduated cylinder or a ruler, whatever, that I expect you to be able to make them. Okay, so if you have a measurement in science, you better have both a number and a unit. Every science class will tell you this. Some science classes don't care as much if you actually put that unit. It's like, we kind of talking about. In chemistry, that's not, you have to put the unit, okay? Don't go fudging that one. Don't be telling me 9 what, okay? 9 centimeters, 9 grams, 9 moles, what are you talking about? So without a unit in chemistry, a number is relatively meaningless. The unit tells us what it is. And for those units, we are going to use the SI system. So the English system is feet, pounds, gallons. We're not really using that. I am going to stick with this system, but you need to make sure you know the SI system and how to use it. SI system is System International. That is meters, grams, liters, those sort of things, and that's what we're going to be using. Okay, base units. The SI system is kind of cool. You only have a few units that are called base units. These units set the standard for everything else. Okay, they're not all the units, but these units are the base, and then everything else is set up on them. Let me try to explain that a little bit. Okay, so what are the base units? Well, you have a base unit for length, mass, time, temperature, mole, current, and luminosity. And I put memorize. Do make sure you know what these are. You probably know some of them, like length. What's the unit for length? Hopefully you're saying the meter. Okay, how about mass? What's the unit of mass? You might have said grams. It's actually kilograms. This is the only base unit that has a prefix on it is the kilogram. It's because the gram's so small, so they decided to make the kilogram the base unit instead. Time is measured in seconds, is your base unit. Minutes, everything else is based off seconds. Temperature. If you said Celsius, you're actually wrong. It is Kelvin, because Kelvin goes down to absolute zero. So temperature in Kelvin. Mole is a mole. We'll learn about that next chapter. Current. This one we don't work with as much, a little bit in electric chemistry, but current is actually measured in amperes. So current is measured in amperes. And then luminosity, that might be kind of a funny one. That's intensity of light, and that is measured in a unit called lumens. Again, this is not one that we really use a lot in this class. Use it a little bit more in physics. Okay, but you should know those and be comfortable converting. Okay, then we have our good old prefixes. So I put some stars on the next page to show you those in a second. You need to make sure you know those and that you're comfortable converting between them. What do I mean? Okay, so right here we have a bunch of different prefixes, right? And these kind of crack me up because you go all the way up from yada. There's actually a unit called yada, you know, yada, yada, yada. The yada is 10 to the 24. It's a huge unit, so we don't use it very much, but it does exist. And yocto, way down at the other end, super tiny. This is down, you know, the level of subatomic particles, really that small. Zepto, atto, femto, pico, nano, micro, whatever. So you don't have to know all of them. I just put them there for your reference, but the stars, make sure you know them and you can convert between them. What do I mean? All right, let me show you how to use this chart. Okay, so 10 to the 6 is mega. How do we use that? Well, what this means is this is put in terms of the base unit. So how you would read this is if you have mega, let's just take grams. Okay, so you have megagram here. Okay, if you had 1 megagram, that would be equal to 10 to the 6th grams. So that's where that 10 to the 6th number comes from. You can flip it if you want. You could say that 10 to the negative 6 megagrams is equal to 1 gram. And I'm sorry, my pen is not the best here. Like that. Okay, so either of those is a true relationship, and that would be true for all of these things that you're going to see here. Same with like nano, 10 to the negative 9. That's the smallest one I want you to know. So if you had 1, so this is in terms of base, okay, so 1 nanogram Ng is equal to 10 to the negative 9 grams. And you can flip that. You could say in the positive 10 to the 9th nanograms, oh, I'm sorry, this is writing so terribly, is equal to 1 gram. Okay? And you can flip it either way, and they're both going to be a true relationship for you. Okay, hopefully that makes sense. Some of these you might recognize, like giga and tera. If you're a computer person, you know what those are, right? They have to do with computers. Okay, that's where they get them from. They 10 to the 12th, 10 to the 9th, those sorts of things. Alrighty. So, a couple more things here. We'll be done just in a second. SI system is, we just talked about that with the base units, but you can also get what's called derived units. And these are going to be some combination of base units, like density. So density, you take mass over volume, all right? So the unit for mass is we'll just go with the gram or the kilogram, and then unit for volume, actually volume is in and of itself a derived unit. Volume is going to be centimeters cubed, cubic centimeters. It could also be called milliliters. It's really the same thing. And that's because if you think back to your geometry class, and you have a box, a cube, and you want to get the volume of that cube, you know you've got to take side times side times side, right? Where side cubed. And that will give you the volume of that object. So volume is 3-dimensional. You have length in 3 dimensions, essentially, and the area that encompasses. And so that's what happens, okay? We don't actually have a base unit for volume. The base unit for volume is you take meters and you cube them. So there we go. We do tend to call it either the milliliter or the liter. 1 milliliter equals 1 cubic centimeter. So there's something you should know. Typically, milliliters and liters are used for liquids, and cubic centimeters or cubic meters, something like that, is used for a solid object. But really, as far as the amount of space that encompasses, it's the same amount of space, if that makes sense. And so make sure, and then put this, make sure you can solve density problems. Other derived units include things like the Newton, the joule, which, you know, we have, oh, but that's a different unit. Well, yes, but if you go in and look at it, like a joule, I get these mixed up, but it's like kilogram times meter squared, second squared, something like that. But there's a combination of base units that make up this other unit called a joule. You could replace this joule with the other units and it would be the same thing. All right. Okay, density problems. So a really simple one is if they give you the mass, if they say maybe you have like 45 grams, and they give you the volume, and you have a volume of 64.9 cubic centimeters, then it's very simple to get density. Just go ahead and divide. So mass over volume, take 45 divided by 64.9, and you should get density is equal to 0.701. Okay, and then units will be grams per cubic centimeters. Like that. So that would be like your simplest problem. Sometimes they can get a little bit more complicated. So if you have like a graduated cylinder, okay, they might, if you have a weird shaped object, let's say like a rock or a piece of metal or really whatever, it might be hard to calculate the volume of that object. And so one common way of doing that is to plunk it in water. So let's say you start out with, say, 50 mils of water, and then you chuck the rock in, and then you have maybe like 75 mils, or, you know, a higher amount. The difference in these, in this case, what, 25? That would be the volume of the rock. So if you plunk it in and it rises 25 milliliters here, then you're safe to say that that rock has a volume of 25 milliliters, or 25 cubic centimeters, and then you just put that into your math equation, and you can weigh the rock pretty easily. So that's another way you can do it. I gave you some practice problems with that on your worksheets and things, and you're welcome to go find more practice if you need some help there. Okay? All right. Last slide here for today, and we'll come back next time with sig, figs, and scientific, your favorite things ever. But scientific notation. So we're going to use either really big or small numbers and try to get these easier to work with. I remember when I really did not like scientific notation when I was a young student, because I said to myself, it seemed like so much trouble. And by the time you went through all that trouble to put it, you know, figure out, move the zeros and do the exponents and figure out what it was, I was like, I can just write the zeros in the time it takes you to do that. That was before I found out what a mole was, and, you know, and how far away, you know, Alpha Centauri is, a star, and how big the universe is. And once you start seeing those numbers, you're very thankful for scientific notation. This is chemistry class. We are talking about atoms, molecules, ions, protons, electrons, super tiny things. And so on the one hand, we have very, very small numbers because they're very tiny. On the other hand, if you're talking about number, you know, the number of atoms in my pen is numbering in the millions, possibly the billions. So many atoms in this pen. And that's a really big number. So we have both really small and really big. It's good to know how to do scientific. So you should be comfortable with that, okay? I'm not really going to come back and teach this again during the year. If I give a number to you in scientific, you ought to know what it is. Or if you are calculating an answer in your homework and you get a really big or really small number, I expect you to put it into scientific notation. Every year I'll have a student at some point in the year, and I get their homework, and it's like a number. It's got like 7 zeros after it. I'm like, put it in scientific, okay? First time, you know, probably won't count you wrong. Second time, might count you wrong. All right, so general rule of thumb for me, this is really just a Miss McNally thing. If you have more than 2 zeros one way or the other, it would be good to put that in scientific notation. So if you have something like, so. Okay, and then last idea for this little video, precision and accuracy. So ideally in science, you want both, okay? If you are very precise and very accurate, put them together, you will do good things in science and good things in chem lab. Sometimes that can be very difficult to achieve both precision and accuracy in your measurements, but we're going to try. So what are these, right? Generally speaking, precision is how close your numbers are to each other. So do I have a big like spread in my data? Like if I make the same measurement multiple times, are all those numbers really close together? Or is there some spread in there? And accuracy is exactly what it sounds like. Is this number like the true number or the correct number? So if I know something is 5 grams and I measure it, is it going to come up as 5 grams, or is it going to show up as like, you know, 4.8 or 5.2 or something like that? That's accuracy. So how do we do this? Well, in science, a scientist is only as good as his instruments. You can be the best scientist in the world, and if you've got a plastic pipette that can't measure very precisely, you're not going to be able to measure very precisely. It's just the way it works. So there is something called precision of the instrument. That is based on how many decimals that instrument can give you. So in other words, if you have a scale, maybe your little kitchen scale or your bathroom scale, and that might only weigh to like the 1/10 of a gram. So let's say you had a 5-gram weight and you put it on there. On your little kitchen scale, you might only get 5.0 grams. Okay? In my scales in the lab, you can get 2 or 3, okay? So my scale in the lab might weigh it out to here. And a really, really precise scale in a bigger lab might even give you 4 decimals here. Okay, so this one is more precise than this one up top. So for an instrument, the more decimals, the more place values that instrument gives you, the more precise it is. But just because you have a precise instrument doesn't mean you make precise measurements, which is kind of funny because the measurements can then depend on the people. Okay, so precision of a measurement is how close your numbers are to each other. Is it repeatable? So in other words, if I measure it one time, I might have got 5.0, and then I get 4.7, and then I get 5.1, and then I get 4.9. Like, they're all around 5, but honestly, that's not that precise, okay? You want your measurements a little bit closer than that. The closer they are, the more precise. Accurate is how close your numbers are to a true value. This can be hard to determine because what is the true value? So usually you're going to check your work based on a known. Is there a known value for this number? And then how close are my numbers to the actual value? Okay? So you have things like you can have one without the other. You can have a precise instrument, but it's inaccurate. Like it's measuring very precisely, but you have a 5-gram weight, and every time it's telling you it's 4.7, and it tells you it's 4.7 every time, very precisely. But it's also inaccurate, okay? Not good, and accuracy without precision, that's almost worthless, but you can have one or the other. Okay, hopefully that helps, gives you a refresher. We'll come back next time and work on sig figs, everybody's least favorite next to stoichiometry, but super necessary part of chemistry. So I'll see you then.